Thank you, Chairman. And let me thank the organizer, first of all. I mean, I don't get ever invited to this kind of workshop. I'm enjoying it a lot. Let me explain briefly where I'm coming from here. I learned a lot of magnetic symmetry doing experiments, initially neutron scattering experiments, and then resonant and non-resonant X-ray scattering, later magnetic imaging, and so forth. So I got to experience quite a lot of different types of magnets. And let me show you where the kind of landscape of magnetism that a neutron scatter writes. Yeah, so by the way, the first part of this talk is published in these two papers. And I'd like to acknowledge my colleague Gautam Gurung for the DFT calculations. The final part is not published yet. So I was saying a neutron scatter view of magnetism circa 2010. So the way a neutron scatter classified magnets is generally based, first of all, on the propagation vectors, because this is what helps you finding the peaks, right? If you don't know the propagation vector, you don't know where to look at the Bragg peaks, or magnetic Bragg peaks. And then you start wondering about intensities and whether the magnet is collinear or non-collinear. And then you can have many cases. So you have gamma point structures. You can have different structures, single K structures that are not at the gamma point. You can multi-K structures, gamma plus multi-K. And on this axis, you can have collinear and non-collinear. Here, there's many types that at that time were fashionable. You know, you can see spin ices. You can see helical, cycloidal, exchange friction, multiferroics, manganites, fan structures, many materials. So anything that is in red has a large magnetic moment. Everything else is not in red, we would call it an antiferromagnet. So, you know, that's a perspective, right? So all the actions in altermagnetism is here in this sector, the yellow sector here. So non-PT symmetric collinear antiferromagnets. Right? So I don't want to talk about altermagnets a lot because we talked about altermagnets ad nauseam. I want to broaden out to some of the other types, particularly non-collinear and anti-altermagnets that are more in that categories of non-gamma point structures. But I want to show a couple of slides on more specifically on ordinary altermagnetism, just to show you the perspective. So this is a very famous slide figure from a very, very famous paper. This paper was published in 1955 and shows the kind of magnetic phases in the manganites. It was followed back by the famous paper equally famous paper by John Goodenough, in which he was proposing the Goodenough-Kamamori rules. Now, if you see all these magnetic structures, and I can zoom in a little bit, you know, they use pluses and minus to show, or black and white. Okay? Do you know why? Do you know why they didn't use the arrows? There is a specific experimental reason. The reason is that they couldn't tell the direction of the arrows for two reasons. First of all, because they use powder diffraction, and powder averaging prevents you from seeing certain direction, and also because they have very low resolution instruments. So the magnetic peaks are all at low angle where you have the worst resolution, and you can't really distinguish peaks that are related, say, by pseudocubic symmetry in this case. So you can never tell the direction of magnetic moment. That's why they didn't use arrows. Now,
so I thought at that time you couldn't print arrows.
Oh, potentially, yeah. Although, no, to be fair, that's not entirely true because some of the Russian papers, maybe they have better technology. Anyway, okay. So my question again, question for the audience: do you know? So if you have a structure like this described with black and white symmetries, do you know what the symmetry of this is? I think it was already discussed in previous talks. It's a Shubnikov group. So Shubnikov group described the symmetry, the way Shubnikov had it in his mind, describes symmetries of black and white objects. And you can have Shubnikov point group or Shubnikov space groups, right? So scalar ordering of this type, time reversal odd scalar ordering, which is what the balls really represent, is like ordinary axial vector, time reversal odd axial vectors. This scalar ordering can be described by Shubnikov groups. However, for given magnetic structures, if you have the same magnetic structure, if you want to use arrows or colors, these two ordering corresponds to different irreducible representations of the parent group, of the crystallographic group. And therefore, they usually correspond to different Shubnikov groups. So the same magnetic structure, if you describe with scalars or arrows, talk about collinear structures, they are different Shubnikov groups. Normally, the magnetic point group for the scalars has a higher symmetry than the magnetic point group for the axial vectors. In other words, has more operators. Okay, so Kirill discussed this already previously. Okay, so what does it have to do with altermagnetism and how these scalar Shubnikov groups relate to spin groups? So the magnetic point group, the way we understand it now, describes the rotational part of the exact symmetry of the crystal, so crystal plus magnetic symmetry. It also describes the symmetry of the allowed momentum space texture. So this would be a momentum space texture generically, and that's described by the magnetic point group symmetry of the crystal plus magnetic structure, including spin-orbit coupling, so the generic textures. So we know that spin groups, as been discussed a lot, describe the symmetry of the momentum space textures in the absence of spin-orbit coupling. Okay? So that's momentum space. What does the spin group describe in real space, if anything? Okay? So the answer to this is simple. It actually describes both the spin group and the scalar Shubnikov groups is the magnetic point group of the simplified magnetic structure in which you have removed the arrows and represent them as black and white scalars. Okay? So that's the symmetry in real space that corresponds to the spin groups. Now, in this sense, spin groups and scalar Shubnikov groups are completely indistinguishable. In fact, I was taught mathematics by mathematicians. They are the same group, because a group is defined by its multiplication table. So there's no difference. So this is not at all meant to be a criticism of the spin group approach. One uses the one that prefers. I know Shubnikov groups, so we prefer to use Shubnikov groups even in the scalar settings, but there are many reasons to prefer spin groups. Right, so basically you take your magnetic structure, you remove all the arrows, you represent black and white. The symmetry of that is the spin group symmetry. And in the next slide, I'll show what actually means more specifically. So we have to go to understand how it works more in the tensorial expansion. We have heard a lot about tensors in this workshop. So the texture and momentum space are naturally described in terms of Cartesian tensors. So for K-K symmetric tensors and altermagnets, we're talking about K-K symmetric tensors like ferromagnets. These tensors have odd rank, and they are totally symmetric in K. So I indicate here the elements of the tensor that are contracted with the wave vectors with Greek indices, and the only Latin indices, I, represent the spin quantization axis in momentum space. Okay, so that's the... Yes?
How do you know that it's symmetric? Because from spin groups, we know.
No, it's...
Here you make an assumption, but if we use...
No, it's just... So, yeah.
Including the spin-only groups, which define the fact that I have collinear structure, infinite rotations around the axis of the...
No, it's not, there's nothing to do with spin groups. It's nothing to do with spin. This is simply the way this texture... so you can decompose the textures into the odd tensors and the even tensors always. And the even tensors, so the ones that... the odd tensors are allowed so they are not allowed in presence of time reversal symmetry. And the even tensors are not allowed in presence of parity. So you just separate them. I'll show you later in the talk. You know this just by simple consideration of time reversal and parity. You don't have to go into higher symmetry to understand this decomposition.
Yeah, but the fact that electronic structure has an even parity, you know from the It's a completely generic properties of a structure that has broken time reversal symmetry. And it is even in the case only if there's if there's inversion symmetry. If there's no inversion symmetry, both are allowed. Yes. But that's the point. In altermagnets which break inversion symmetry, still the band structure will be even.
Not necessarily. I'll show you in a second that is not necessarily the case.
And this is the property of the spin-only group which defines
no, no. Let me carry on. I'll explain this later. Okay. So one can define an even rank tensor. So that's an odd rank tensor. One can define an even rank scalar tensor so that when contracted with K gives a scalar, and decompose that tensor in this way. Okay. So you can decompose the odd tensor into an even tensor times the components of the staggered magnetization plus everything else. Okay. That decomposition, so this tensor transforms with a spin group or with a Shubnikov group because they are same groups, they have the same effect. And note that this tensor here, so the residual part, can also have components parallel to L. So it's not just, this is not just all the components parallel to L. Okay? This tensor has higher symmetries, as I explained before, and this tensor defines the part of this tensor that is allowed in the absence of spin-orbit coupling. So to me, this is the essence, the quintessence of altermagnetism, the magic of altermagnetism. This is the composition. So it's decompose the tensor in two components, one that's allowed in the absence of spin-orbit coupling and one in the presence of spin-orbit coupling.
Okay, can I ask?
Yes?
Okay, so is this for also non-collinear magnets?
Non-collinear, I'll show it in I'll show the equivalent formula in non-collinear magnets. This is just altermagnets.
Collinear, right?
Collinear, yeah, so I define the classic, I don't deviate from the classical definition. Altermagnets are collinear.
But how does the mathematics know that it's collinear?
The mathematics know it's collinear because it's, that's the way, I'll show the corresponding formula for non-collinear and that becomes obvious. Okay. So these groups, the fact that you basically apply Shubnikov group, that's intrinsically, so if you can make the substitution, collinear spins, black and white, that's only possible for collinear spins. And I'll show you how you do it for non-collinear spins. Right, anyway, so if there's no, I hope if there's any controversy on this, let's get it out because that's the basis of what I'm going to say. Yeah.
Just a quick comment. I think the form of the first term is equivalent to the spin-only group. I mean, it follows from the spin-only group applied on top of
So there is a spin-only group.
the first term. Yeah, postulating the first term is equivalent to applying the spin-only part of the group.
It's not in
Yes.
Shubnikov group. That's the point.
Yes, that's right. That's right. There's an additional.
No, that's not true. That's not true. It's a scalar Shubnikov. It's not the magnetic point group. It's the scalar Shubnikov that is the magnetic point group of a hypothetical structure in which instead of having axial vectors, you have time reversal of scalars.
But sorry,
But you have nothing in this slide depends on the Shubnikov group, I think. The first term is the assumption of collinearity.
Yeah.
And that's the spin-only group.
Yeah. So that term here, so the whole term, as well as this term here, transform with the magnetic point group in the way we understand the magnetic point groups, right? The one that acts on axial vectors.
I think the only point that kind of made a little bit is that the spin-only groups, they're not right now. You're making, when you deal with the Cherenkov, it's assumed that the spin-only groups is kind of there, but the spin-only groups have an important role in there in the case of the fact that all band structure without spin-orbit coupling will be even, irrespective of whether they're breaking parity or not. That is a fact, and that's actually not. That is a fact. Paolo.
I know.
That's all, and that itself, the Shubnikov group does not do that.
The action of the scalar Shubnikov group and of the spin-only groups is the same. It acts absolutely the same.
But it will not predict.
It's
The non-trivial.
the non-trivial. The non-trivial.
Yeah. That's what I'm saying. That the non-trivial is a one-on-one, but the product is with the spin-only group, and that spin-only group has some consequences.
Okay.
That's the only thing.
Okay,
That's
we
important.
will see if anybody we can discuss it further, but let me carry on with the okay. So there was a lot of talk about. Sorry, yes.
The odd rank tensor, does this refer to having only I or an odd number
There's
of
the
A?
odd rank
of,
including I. Okay, so so there's always an even number of wave vectors contracted with that tensor.
And why?
Because that's the one that is allowed in the presence of parity and not allowed in presence of high reversal symmetry. It's simple parity and time reversal considerations.
But why is that parity?
No, there doesn't need to be parity. There doesn't need to be. Parity has no effect on this. Parities has no effect on this. Okay, so because
maybe we
parity has no effect on this. Parity has absolutely no effect. Parity has no effect on any of this.
Okay, let's listen.
But it's allowed to exist. Yeah, okay. Yeah. Let me carry on. Okay, so just very quickly, because I have other stuff to talk about. So, so we talked about macroscopic properties, and I just wanted to emphasize, that the different altermagnets have, for example, in these two cases, these two famous cases we discussed, cobalt fluoride and Fe2O3. They're both altermagnets. They're both piezo-magnetic. Alpha Fe2O3 has two phases. one in plane and one out of plane phases. That was discussed in this paper by Jaroszynski a long time ago. So we already have discussion about these. I just wanted to point out that in a C-axis phase of Fe2O3, there's no piezomagnets in absence spin-orbit coupling, being a G-wave. And however, at room temperature, in the coplanar phase, there was weak ferromagnetism, XMCD, topological structure, and many other things. So, right. So I want to generalize now to non-collinear structures. That's the main. So I showed the case of collinear structures, and now how do we generalize to non-collinear structure? Why is it important, first of all? Okay, because there was a lot of work was done in non-collinear structure in the past, and there was already remarked that they are similar to ferromagnets in many aspects. There's charge currents, there's spin polarized charge currents, and also transverse spin currents in the absence of spin-orbit coupling. So these kinds of concepts were developed, in fact, before the important discovery that collinear magnets have similar properties. And also people discussed, okay, this is the way this is discussed. They talk about large anomalous Hall effects in some cases, etc. So how do we generalize? Well, so if we start from the point of view of scalar Shubnikov, which is black and white symmetry on scalars, there's no reason why these permutations should be limited to 2 colors. So we have black and white. Why not 3 colors? Why not 5? Okay. So the theory of color groups is well developed, and in fact is better known in the Escher drawings, of which I'm going to show one in a second. One can also completely equivalent using non-binary spin groups. Okay, in which the rotations are, instead of being by pi, they rotate by fraction of pi. Again, it's completely a matter of choice whether you use non-binary spin groups or color groups. So the altermagnetic light textures, that is the one that don't depend on spin-orbit couplings, are constructed with this method, and they are rotationally invariant by construction, or rather, to be more specifically, they are co-rotating. So the textures in momentum space rotate rigidly when you rotate all the spins in real space around a given axis. That's the required property. So how do we actually do this? Instead of just having one component of the staggered magnetization, you just put more components, right, which represent the different direction of the non-collinear structures. So I call this altermagnetic-like, okay? So, these components are associated with different colors. So they're scalars in the sense they don't have a direction, because you want to pick up the non-directional components, but they have to have different colors because the symmetries permute these in a complex way. So how this is done, so you sum of the colors, essentially. So this is an example of, I just want to show this because it's so beautiful, right? So this is an Escher drawing. It's a 3-color symmetry. That's a unit cell. The small one is unit cells in the absence of colors. So if everything was gray, this is larger unit cells, so it's actually called a lattice. And there are different permutations. The color, for example, you see the 6-fold axis permutes yellow and blue, but keeps right the same, for example, in this case, okay? And so forth. So you can play around it. The symmetry is P6 in the absence of...
I have a question.
Yeah.
So, okay, for most of the magnets that we all know and love, all of this will work. There is this hypothetical state that I don't think has ever been observed, or maybe has not been detected. It's called the spin nematic, which has is characterized by a triad. It's a tensor in spin space. Okay, how will that fit into this?
Okay, so that's my next research project. I don't know. Anyway, this works.
This is an important, because people have speculated about how to detect that, say, neutron scattering and things of that sort. Okay.
I mean, spin nematic phases can be detected because there is a director field associated with them, right? So that's definitely possible. Okay, so how do you actually do it in practice? Well, you replace the unique real space moment direction, Li, with unique colors and determine color symmetry groups using the well-known procedures, which I'm not going to explain. You construct colored scalars in the same way you construct the black and white scalar before, and the symmetry interchange the scalars. So if you have 3 colors, you interchange 3 scalars. If you have directions that are opposite to each other, you can use the same scalar because it's time reversed, essentially color anti-color symmetry. And then at the end, you reassociate each tensor with the corresponding vectors and reassemble the full spin texture. So what you get is by construction, the totally invariant, the co-rotating part of the texture, like in altermagnets. Yes.
When you have moments in the unit cell which have different magnitudes.
Yes. Potentially that works, and I couldn't find an argument of why it shouldn't work. You can still do it. So it's very important. I thought a lot about it. And what if the directions are not related by symmetry? Because you're not picking up any particular. So that's an interesting question. Yes.
I think you need separate color sets for each orbit.
Yeah. Yes, that's true. Of course. Yeah. So yeah, that's right. Anyway, so I'm just showing you how it's going to work with a very well-known example. These are the antiperovskites, right? So the antiperovskites are antiperovskites. The magnetic sites are what the oxygen site were in a perovskite, and this is manganese gallium, manganese 3 gallium nitride as an example. And what I'm doing here, I'm showing two of the phases. The gamma 5G, they're all gamma point ordering. And you can see there are Kagome lattices here. And the two phases differ, the gamma 5G and the gamma 4G, just by a rigid rotation in spin space. So you rotate all the spins by 90 degrees around the one axis of the cube. And then you get one to the other phase. So they should, altermagnetically speaking, they should be the same, because the two phases are related by rigid rotation in spin space. So you expect to find the same textures, except for the quantization directions for the two phases. Okay? So note that this phase, I showed the magnetic point group, actually that's a magnetic space group. This phase is ferromagnetic, or rather, it allows a ferromagnetic moment. Okay? This phase doesn't. Right, so that's the Fermi surface, rather complicated. I'm going to show, first of all, the DFT calculations done by my colleagues for the two phases, without spin-orbit coupling and with spin-orbit coupling. Okay, so these are the different bands as you cut the Fermi surface perpendicular to the 111 direction. And you could see, of course, that the quantization direction alternate or rotate around the various sheets of the Fermi surface, right? So another thing you can find is that these two are indeed related by a rigid rotation of the spins in spin space, as you expect, in the absence of spin-orbit coupling. So you don't have a collinear structure, but still this rule is preserved. Also, there's no component along the 111 direction. So everything is in the plane because the spins were in the plane. And since the textures are constructed by using the LIs, and all the LIs are in the planes, that spin textures must also be in the plane. If you have spin-orbit coupling, these two become subtly different, and also you have a z-axis component allowed. Interestingly, and I'll show it more in a second, the gamma 4G, the one that's allowed to be ferromagnetic, has net spin Z component. Okay? So, for example, this band here has a predominantly yellow color. Well, yellow means out of the plane of projection. Okay? Whereas here you've got colors, yellows and blue, but they compensate in each band. So I can show it a little bit by showing the fits to the tensors. So what we've done is constructed the tensor up to rank 20 or something and fitted this. In reality, there are very, very few parameters to worry about, because a lot of these tensors are zero and the tensor components are small. So here what I'm showing is that tensor fits to the radial component, tangential component, and axial component. Okay? So the radial component is the component of the spin textures along the radius, tangential, and out of the board. Okay, so this is in the absence of spin-orbit coupling. There is no axial component, as I explained. And these two, see, the tangential and radial are simply inverted. So the dashed line is the tensor fit, and the blocks is the DFT. So you see, they agree perfectly well, right, with very few parameters. Here is the spin-orbit coupling, and you can see you develop an axial component, and you can see in the gamma 4G there's one color for the axial component, at least for that particular band, which means it's basically it's ferromagnetic, weakly ferromagnetic. Okay? So that's the procedure. Band structure, spaghetti plots. One thing is interesting is looking at the gamma R direction, so the one that's along 111, because it's a high symmetry direction. And since it's K-K symmetric, if there's a component, there's a splitting there, is also ferromagnetic. it cannot, there's no, you've got the spin here and then the spin on the other side. So there's no way to permute the spin anywhere. Basically, in the absence of spin-orbit coupling, there is no splitting of the bands along the gamma R direction. And in presence of spin-orbit coupling, there's also only splitting in the gamma 4G, which is the one that allows ferromagnetism. And it's all as expected, okay? Right, okay, let me move to anti-altermagnetism, unless you want to ask a question about the color stuff.
I'm colorblind.
Okay. Well, so am I, but I can see yellow and blue.
So for the black and white, what if I have different magnitudes of the moments? Would that mean that you will also need more colors? But for the spin groups, you don't. So how can there be a one-to-one correspondence? Right?
What do you mean you don't?
I can use the same spin groups also if I have different magnitudes.
The spin groups can be the same.
Yeah, but the color groups will be different.
One thing is the symmetry group, and one thing is how many colors you need, right? So, so if you have different sublattices, you may have the same transformations with different moments.
Okay.
So Paolo, when you're switching the colors between the black and white only, that's to you one operation, one symmetry, right? The time reversal symmetry.
Yeah, it's the same thing as doing the twofold rotation. It's the same thing.
Yeah, but those are two distinct symmetries. And then this is the symmetries that will sorry. What I'm saying in yours is not. No,
in the way I use them, the same operation.
But the spin-only group that has those as two distinct symmetries, because the inversion in the spin and the time reversal in the real space sector, and then its inversion of a spin in the spin sector, but also the C2 rotation, combining those things, that, for example, tells you, which is, I don't see how you would get it here, that in a collinear system without spin-orbit coupling, all band structures will be even. And that's something that I don't understand how I would get it from the Shubnikov's groups only, because it only has the non-trivial part of the spin group. So without that spin-only part, it will not give me that information. And I'm also thinking back ahead, or thinking a bit ahead on your talk on the anti-altermagnets. We have in the P-wave coplanar systems a unique property that for the coplanar systems, the exchange, you're going to have a polarization in the out of the plane due to the spin symmetries. And that's the thing that I would like to see if you are extracting that from the color ones. That's the question.
The way I understand it, I mean, perhaps there's more to think about, but the way I understand is the following. Because you're using, so the operation of your symmetries are on scalars, or time reversal odd scalars, parity has no effect on time reversal odd scalars, okay? Unless you're changing, but the two sublattices are never related by inversion. So in a way, it doesn't matter if you have or not have inversion for those type of textures. If you...
Yeah, I will have to...
Okay, right.
At the moment, I don't see...
Yeah. Okay, let me just generalize to anti-altermagnet. So that's okay. So that's what I've done for altermagnets. So you have a staggered field, which is the difference of the field on the two sublattices. You create your tensor here, and then you have, and this tensor is contracted with an even number of wave vectors. Okay, the odd tensor has one free component, the I component, and contracted with an even number of wave vectors. And then you separate it out this way, as I've shown before. Okay, so you would like to be able to do the same for the even tensor, so the one that are contracted with the odd part. So remember, it would be the same type of textures that you get for Rashba-Dresser-Haus. Okay, so can I do the same analysis, but extracting the part that doesn't depend on spin-orbit coupling? And here it was completely inspired by the work that was done by Hanna and Libor, etc. But I just thought about it in a different way. So can I do the same decomposition for the odd part? The odd number of wave vectors. rather than an even number of wave vectors. Okay? So can I decompose it to an anti-altermagnetic part plus a residual part? And this altermagnetic part will have the property of being co-rotating with the spin system. So if you rotate rigidly the spin system, that part will co-rotate with it. Now, let's think a little bit about it. What could be the psi field? So the equivalent of the staggered field. It has to be time reversal even and parity odd. So this is time reversal odd and parity even, but psi has to be time reversal even and parity odd. So the only real choice for this is the cross product of two radiation spins, which is time reversal even and parity odd. Okay? So the staggered field is this, and which is inserted here, and this altermagnetic tensor will be the equivalent of the altermagnetic scalar that I showed before. So this is the equivalent of this object here. Okay, so looking at correspondences for K minus K symmetric, that is altermagnets and non-collinear equivalent. This is the collinear case so the structure is collinear, it's symmetric in K minus K for altermagnets, and it's coplanar, and the exact equivalent, so a single staggered field is the coplanar antisymmetric K minus K antisymmetric part. The forbidden symmetry in both cases, it's T in one case and P in the other case. So if there's T, there's no altermagnetic textures. If there's P, there's no anti-altermagnetic textures. The scalar, the rank is odd even in one sense. So the vector tensor is odd, and the one that's contracted with K, the scalar tensor is even, and the two are reversed in the other case. And the staggered field in one case is the usual staggered magnetization, and the other one is the cross product. So the tricky bit that I had to think a little bit about, how do you construct the equivalent of the black and white representation, that is the scalar field in real space that you want to transform. Right, so by the way, you can generalize also the anti-altermagnetism to non-coplanar, but I haven't done any examples on that, okay? Right, so again, you would have colors and some of the colors, but it's basically a black and white thing. So I just want to show a couple of examples of this to show how that is done. So okay, that's a famous example introduced by Hannah Lenes, and other people have talked about it. The models have been constructed. So the first thing I notice about this is that inversion is broken by the magnetic structure, and in fact, it's very closely related to type 2 multiferroics, in that you have two cycloids running in 90 degrees from each other. So you expect a polarization, if this was an insulator, in the y direction. Okay? The other things about the structure is that it doubles the unit cell. Okay? So it is actually, in the point group, it has T symmetry. So if you look at the texture alike by the magnetic point group, they are the Rashba type textures, as you expect, because it's a polar. So it has two components, XX and XZ, the SY is 0 in this case. Now, I take the structure, and so that's the structure. I want to replace it with a scalar structure, and the way I do it is I introduce bond directions. Okay, so this is a scalar structure because it's a parity odd scalar, right? So that's the way I do it with arrows. I thought about doing with the pseudo scalars, but it doesn't work. So forgive me about that. I limited all those spins. I just leave the direction of the bonds, and the direction of the bonds is the one that gives me a given direction of the staggered field. Okay, so the cross product is one direction between adjacent spins. And I simply look at the symmetry of this object. Okay, so this object is left invariant by rotation. So same field by rotation along x. It's reversed by rotation along y and z. And the way improper operators act is always opposite. Okay, so if you have a twofold axis in one direction, that it preserves the structure, the mirror plane would reverse it. Okay? So again, you can see this is a one-dimensional real representation, which is described by Shubnikov group. But the Shubnikov group is bizarre because, in fact, the primes where normally we think about time reversal, in fact, they are parity, right? So they're parity acting on the field. So I use this little circular hat instead of primes to indicate this particular type of anti-identity. Okay, and from this I can simply construct the tensors. I actually get them from Bilbao because it's a Shubnikov group, and I construct the textures, the anti-altermagnetic textures. This part is now forbidden, so I only get this. Okay, and this is exactly the P wave. In fact, I went to the third rank, so I get the anisotropy as well, because it's orthorhombic. So that's the P wave case. There's another, so there's an anisotropic P wave. There's another famous example in the literature, which is the triangular lattice. Okay, that was presented in this paper, 2020. This is a compound, but there are many triangular lattices. And again, they said that there are textures of this type without synovic coupling. Okay? And you can see they are anti-altermagnetic textures because K and minus K is antisymmetric. Okay? So you do exactly the same analysis. I remove all the arrows, and so the magnetic moment. Oh, one thing is interesting. Sorry, I want to go back to this. That the scalar field is a gamma point. So it does no longer doubles the unit cell. Okay? So we remove that. You see, this and this are always the same. That's also true for the triangular lattice. This is the actual spin structure is a triple K, and that's the unit cell. But the staggered field, so the bond-ordered field, is at the gamma point. And you just do the symmetry analysis of that staggered field, and I get an F wave. So that's the form. So there's no linear term. There's only the cubic term. And I get an F wave, which is exactly what they found. Okay? So this was already in the literature. I just want to show an example that wasn't, yeah.
So there is no time reversal, right?
In this case, there is time reversal, but that's due to the translation in the other direction.
No, in that model.
No, this single plane has no time reversal,
Okay,
but the material itself, when you go to the one unit cell in the z-axis, it reverses the spin. So there is time reversal in the three-dimensional structure. There's no time reversal in the 2D structure. Okay, so just another material. This is called langasite. It's quite famous. It's interesting because it has a very complicated magnetic structure. So it has a triangular chirality in the planes, and then these form helices, incommensurate helices. But you know the staggered field doesn't care whether it rotates, the field rotates. So in fact, it also collapses to the gamma point. You see you have a helical component, and you have a triangular component. Not helical and cycloidal is the same from the point of view of anti-altermagnetism, because a helix and a cycloid are related by a 90-degree rotation in spin space. So in essence, what you get doing the same analysis is a combination of an isotropic P wave and F wave in this case. That was my final slide. Thank you very much.
Okay, thanks a lot. Are there questions, comments to share?
So what is the general rule how to define these bond vectors?
Okay, so the general rule is that that I can show it here, right? So the cross, in order to define a cross product between two spins on different sides, you have to decide what's spin number 1 and spin number 2. Okay, so this is coplanar, so the cross product is always either up or down. This is the bond direction that gives the cross product up. That's the rule.
Okay, also, so the up direction is from the bond direction.
Yeah, the bond direction defines that the staggered field is always in one direction. Yeah, that's yeah. Yeah.
So it's sort of magnetic K line.
Sorry?
Yeah, it's a Riemann something. Okay.
Yeah. Anyway, that's the way I thought it could be done, and it works actually. So empirically. Well, no, I mean the symmetry is correct, right? So this field, this is a scalar field, and if you construct the tensor from that scalar field, you get something that is indeed invariant by global rotation in spin space. And it's very nice because you can see that so if I go back to here, you can see that I eliminate one component, but the other component stays. So the general textures that are allowed by the magnetic point group. So the anti-altermagnetic texture is a specific example of that.
Thanks. So, and second question, did you try to check one of these Nicholas materials, like cobalt neop-free sulfur 6, which is non-coplanar?
Yeah, I mean, that's exactly, so the way I thought about doing it is just using colors as in the other case, but
because that's the interesting prediction from the spin groups is that the bands are degenerate without spin orbit, even though it's type 3 magnetic space group,
Yeah.
which
Okay.
broke.
But you're saying that this is because there are 3 axes of rotation.
Yes, exactly.
I mean, this is an important that's an important consideration that rules out, for example, collinear structures. So a collinear structure, even if it breaks parity, will never have textures that without spin-orbit coupling, and because there are axes, there are 2 axes in this case, that you can rotate these spins and reverse the texture. So that's a consideration. I think Sang made that consideration. I heard him for him, but it's kind of very natural. So a collinear structure always invariant by rotating around the axis, and then when it has time reversal, that's another axis. So yeah.
So thank you very much, Paolo. Now, maybe can you tell us maybe advantages of using this notation with respect to using like spin groups and so?
Right. So okay. In the case, you know, I hear what people are saying in the back. For me, in the collinear case, they are completely identical. There's no other advantage. I mean, I stand to be convinced that there are, but for me, it's the same group, the same transformation, and having time reversal as a separate operator, I don't really understand why that is advantageous. But
The non-trivial spin groups.
eh?
The non-trivial.
Yeah.
That's what they are identical.
Yeah.
The non-trivial.
The non-trivial part.
But
Yeah.
kind of keep on emphasizing that the spin-only part.
Yeah.
It has a consequence.
Yeah.
And then that is an assumption that you make, and then you use the black and white, which is fine to do. But you already exploited that other part, because that predictions involved with it, similar to the color in the anti-altermagnetism.
Yeah.
You can also use the spin group.
Yes. Yes.
It automatically also comes very directly.
Yes.
But
It does.
the planar is also very.
Yes.
And I see it much.
Yes.
For me, it's much more difficult with the technicolor. You know, I'm not.
Yeah.
sure why,
Well,
but
yeah.
But for me, it would be difficult.
It's-
But I'm sure it does.
Yeah. So for me, so in the case of black and white and binary spin groups, for me is the same. I don't see I've made any assumption, but maybe I have. In the case of the colors, that's more subtle, because the spin groups always make spins equivalent. So the color is always associated with equivalent, because you're rotating actual spins in real space, then the colors are always equivalent by symmetry. Right? So in fact, the referees asked me exactly the same question: why do you use colors and not spin groups? So so the construction works so when you've chosen the color, you don't have to have spins that are equivalent by symmetry or even equivalent in length. So the question is whether this is physical. If it is physical, then there's an advantage using colors. There are structures that have non-equivalent non-collinear spins. Perhaps they have the same length, but they're not obviously related by any space rotation. So I gave one example in the paper. Whether this is really physical or not, I'm not entirely sure. In most cases, all the examples I've given, the spins are actually internally related by a rotation. So you can use perfectly the spin group approach, naturally spin group with not the binary spin group, but ternary or quaternary and so on. So that's fine for me. Other ones is a matter of preference. I know Schuppenkopf groups by heart. There are lots of people that don't like this new notation, or lots of people that do like the new notation. So it's, for me, it's a question of where the tradition is coming from, and color group actually were used in the past to describe magnetic structure. I didn't invent it.
No, we didn't invent spin groups either.
Exactly. Yeah. They've been there a long time. All these things have been there a long. And it's sort of kind of nice. I really like the Escher drawings, right? So I said, well, cool. This stuff. For once, I have found a way to apply something so beautiful.
Okay, are there other questions? No? Okay, I don't see that this is the case. Then let's thank you.